All right, grade 12 chemistry. We're talking about practical thermochemistry today. So this is some, ways that these concepts are used in industry and in theory. Here's our goals. We're going to talk about multi-step reactions and rates. We're going to talk about determining rate law, talk about the effects of catalysts, and then we'll talk about energy density and some environmental issues involved with energy density. Jumping right in, let's talk about the rate determining step. The rate determining step. Here, what we've got for the rate determining step is you have to think of a reaction that has multiple steps. So for example, this is a two-step reaction, right? A plus B plus C to ABC. Maybe A and B get together first, and then A, B, and C get together to make ABC. And the concept here is that some of these steps are slow and some of these steps are fast. These steps are slow and some of these steps are fast. And the determining step of the whole reaction, the blue reaction here, depends on the slow step. One really good analogy for this is like pouring water into funnels. And the small funnel obviously can't push as much water as the bigger funnel. And it doesn't matter where in the sequence the small funnel is, right? The small funnel determines how fast you can fill the Erlenmeyer flask down here, no matter where it is in the sequence. So that's why we say it's a rate determining step. It can be at the end, it can be at the start, but it's going to slow down whatever you've got. Or another example, frequently used is traffic on the highway. Here I've just got someone in the Tour de France. This car can go way faster than this bike, but the bike's in front of the car, so he's determining how fast the car can go. And if you drive, you know that sometimes this happens. You're just stuck behind someone going slowly. That's your rate determining car, your speed determining car, I guess. This is a rate determining step. So looking at this diagram here, why do you think this one is slow and this one is fast? Take a second to think about this energy diagram. Why would this one be slower and this one be faster? If you said something about activation energy, you are correct. If we look at the activation energy on these, this one has quite a high activation energy, so it's a big hill to climb before we can fall down here. This one has a much smaller activation energy, right? A smaller activation energy. So this is a slow step. This one will be much faster at the same temperature because it's fast. Also, it just fell down, so it's got plenty of energy to come back up the hill. So that's the rate determining step. And here's a little practice problem about that. So I'm going to move my thing over here. Indicate the transition state of the rate determining step. So remember the transition states happen here, 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 and here. It's also this one's also asking us whether the overall reaction is exergonic or endergonic. Remember that just means whether delta H is positive or negative for the overall reaction. And so this one here, we have an overall exergonic reaction. This one here, we have an overall, well, here's the final, right? So the overall is actually endergonic there. Yeah, so exergonic, endergonic. So which one of these is going to be the rate determining step? Is it this transition state or this transition state? Well, let's look at our activation energies. This one takes this much energy to get to the activation, to get to the transition state, and then it falls down. This one takes this much energy to get to the transition state, and then it can fall down to the final product. So this guy is going to be the rate determining step. This reaction here is the rate determining step. So that's the step. This is the one, right? That's the rate determining step there. Meanwhile, on this one, we have this much activation energy here, and this much activation energy here, right? That one looks taller, so we're going to go ahead and say that it's this guy. This guy's the rate determining step. That's the rate determining step. The first step on this one and the second step on this one are the rate determining steps. So that's the concept of multiple steps and the rate determining step. Yeah. Next is reaction mechanisms for organic reactions. Here's an example of a two-step reaction versus a one-step reaction. I'm going to talk very briefly about this. I'm talking about this stuff just because I like organic chemistry. This is a substitution mechanism. This one is going to come in, kick out this one, right? This nucleophile is going to kick out this nucleophile. You see how it kicks it out? You can do it in one step, which is confusingly called SN2, when this one comes in and just kicks this one straight out. So it's just like boom, boom, like those Newton's cradle, the ball things, right? It just comes in and kicks the other thing out. So that's a one step. Or it could happen in two steps, where this one will leave. This one will just kind of leave. Maybe it's attracted to something else in the solution. And then the second one now has an open space that it can jump in on. So that'll be a two-step process, because this one has to leave first, and then the second one has to come in. And we know that it happens because if we do this reaction in a certain condition, only this reaction can happen, and we always get this stereochemistry. Because the thing had to come in and attack from the back. It's literally called a back attack. So this comes in and attacks from the back. We always get this stereochemistry. But if we do it in different conditions, we get the two-step process where this leaves, and when it leaves, this turns into trigonal planar, and then this nucleophile can come in from this side or from that side. It doesn't matter which side it comes in on. So we end up with this mixture of isomers, this mixture of stereoisomers, which we don't get when we do it under these conditions. So kind of proof that transition states exist, proof that this thing, this intermediate actually exists, proof that this has to come in and attack from the back. Even though we can't actually see it happen, we can infer what happens from these studies. And here's just the concept of a rate limiting. Here's the rate limiting step, this one here. The rate limiting state is here because that's the highest activation energy. This activation energy is quite high. This one's very, very small. So it comes up here, and as soon as it comes down here, it's basically going to go down to the next thing. It's very, very fast. This one here, just one step, so that is obviously the transition state, this thing. And again, we can infer that it exists from what happens, from the fact that we get no mixing on this one, but mixing on this one. Yeah, that's pretty cool. Now we're talking about the rate law. This is kind of cool. This comes from, I'm going to pause and set some stuff up. Usually these come from experiment. The rate laws come from experiment. And it's in moles per second or moles per liter per second. So how fast can you make something? Or how fast do you use something up? Like this one, for example, moles of NO2 formed per second, or per liter per second, because it's a gas. So you could get it as a pressure as well. There's a bunch of different ways to get a rate. But the rate law here, this is a constant, K is a constant. These brackets mean mole per liter. Mole per liter, that's what the bracket means. The bracket means moles per liter. Bracket means moles per liter. And in this case, what they noticed is that it's related to the square of the NO, and just the square of the concentration of NO and just the concentration of oxygen. So if I double this, I'll quadruple the rate because it's the square. If I double this, I'll just double the rate, and so on and so forth. One thing that's interesting is it doesn't depend on the coefficients or anything. It just is experimentally verified. So for example, this one here, we got 2N2O5, but it's just a first order reaction, we call it. It's just related directly to the rate of this. If I double the concentration, I'll double the rate and stuff like that. Same thing with this. And sometimes it's even fractional. This one, it's related to the square root of the bromine concentration. So to the 1/2, the square root of the bromine concentration. So yeah, the rate law can help us understand how these mechanisms proceed, because we can figure out, if it's a square, maybe it takes 2 molecules instead of 1, things like that. Everything follows it. We got a rate constant K, and K is determined by using concentrations in moles per liter. So you can find tables of the K of various reactions, and it also changes with temperature because of how much energy there is. So we can actually figure this out empirically though, and this is another little kind of problem-solving thing in chemistry. Here we have our starting, we have 0.35, 0.35, and 0.35 of A, B, and C. And here's the rate in moles per liter per second. When they do the green reaction here, all they've done is doubled, right? This one has doubled, times 2. We have doubled the amount of A. 2 times the amount of A. And let's look at the reaction rate. The reaction rate went from, let's put this into not scientific notation just to make it easier for us. That's 0.008, this is 0.0032. And we'll just keep doing that, 0.0064 and 0.0032. Right, so when we double A, what happens to the rate? The rate goes times 4. Right, so they doubled A, but the rate went up by a factor of 4, which means that it suggests that we have rate equals K, and then we're looking for the coefficient for A. And in this case, what this suggests, because we doubled the amount of A, but this went up by a factor of 4, is that it's A squared, because when we double A, it went up by 4. So 2A to 4A squared kind of thing, right? Because we doubled it, it went up by 4. Then what did they do? Well, they played with the amount of B, right? They kept this the same, so that stayed doubled. So that stayed doubled, so we expect the 0.32 to stick around, but then they also doubled B, right? They doubled B times 2. And when they doubled B times 2, from this rate, it went times 2. So it followed what they did to B. They doubled B, the reaction rate doubled. And so we add that into our rate law thing, and B. It's just going to be B, right? B to the 1, basically. I'm going to write in B to the 1, actually, and I'll bring that down. B to the 1. B to the 1. And then we're going to look at C. What happened to C? When we look at C, they kept the same A, but they brought the B back to the green level, right? They brought the B back to 0.35. Right? So we expect then that the rate is going to, the basic rate is going to be 3.2. 3.2. And then they doubled this guy, right? They doubled times 2. Times 2. And what happened there was nothing. Nothing happened. 0.7, 0.7, 0.35, 0.35. This doubled, but the rate didn't change, which suggests that C doesn't affect the rate. Changing the amount of C doesn't affect the rate of the reaction. This can happen when it's like a solid reactant. It can happen when it's a liquid. But essentially what we're saying there is that it is C to the 0. C to the 0. And if we rewrite that correctly, because an exponent of 1, it just sticks around. So it's going to be K times A squared times B. A squared B. And that's it. That'll be the rate of this reaction. We can even work out what K is if we do a little bit of math, right? Put in the concentration of A, put in the concentration of B, and then have the rate, and then just rearrange for K. I'm not going to do it because, I feel like you guys have enough algebra skills to figure that one out. But you could figure out what K is as well just by putting in the numbers. Plug in, 0.35, 0.35, and 0.35. Plug in 0.0008, and then you can solve for K if you want. So yeah, that's determining the rate law. Next up in our thing is catalysts. So I'm going to pause and get the catalyst thing going. Before I jump into catalysts, I went ahead and calculated it. So you basically take this, put in 0.08, 0.35 for A squared, because it's A squared, 0.35 for B, normal because it's 0.35. C doesn't matter because it's not even in our reaction thing. And then multiply those together, and yeah, there you go. K is 0.019, and that K should stay the same for all of these. You can verify that if you feel like it. Yeah. Next up, catalysts. So how do catalysts affect reactions? The big thing is catalysts will change the mechanism, but they won't change the overall reaction. And I'm going to bring that down here. So there's two basic ways that a catalyst can affect a reaction without taking part in the reaction. The first is holding the reactants in the correct orientation. So here's an example of platinum doing the hydrogenation. So remember, hydrogenation is when we take an alkene and we put hydrogen on each side of the double bond. Basically how this works, the platinum is holding hydrogen, and it just holds the hydrogen exactly the right distance apart so that the alkene can come in and grab the hydrogen and go. So the platinum here is just acting like a surface. It doesn't participate in the reaction, but it's holding it in the perfect orientation, so it makes it more likely for an effective collision to occur. It's changing the mechanism. If this were happening in just, in solution or in gas phase, you'd have to wait for the hydrogen to bombard the ethene, but here it's right there on the surface and the ethene's going to come in. And the other way they can do it, enzymes will do the same thing. Here's an enzyme. It's just a big molecule. It's an enzyme. And this is catalase. It takes hydrogen peroxide, 2 hydrogen peroxides, and turns it into an oxygen and 2 waters. And there's an active site in here where the 2 peroxides will come in and get kind of rearranged. The enzyme is not changed by this process. It pulls in the peroxide, does its job, and then kicks it out, and then can do another peroxide, another peroxide, another peroxide. It creates this perfect orientation. Yeah. Then the other kind is acting as an intermediate step, which makes a faster overall reaction. So instead of one step, you make multiple steps for the reaction. It's kind of like providing stairs, right? I'm on the 2nd floor of my house. If I didn't have stairs, I wouldn't be able to jump up here, right? But I do have stairs. So instead of making one big jump, which would take too much energy at once, one big jump that would take too much energy at once, I can climb the stairs. So I've got these intermediate steps. And the same thing can happen with the hydrogen peroxide reaction. Here's the normal reaction. It's slow, but if there's iodine in the solution, you get hydrogen peroxide plus iodine. You get this ion, and it makes a water. And then a second peroxide can come in and react with the ion, this OI ion, and make another water, make the O2, and then it regenerates the iodine. So this is the kind of important thing. The iodine forms a closed loop. The iodine will then come back and you can start the reaction over and over again. So you've got a catalyst. It's an intermediate catalyst. It's just going through the reaction over and over again. And it's regenerated. So often people will say catalysts speed up the reaction without taking part, but they do actually take part, right? That's why I put taking part. That's why I put taking part in brackets up here, because they do actually take part in the reaction sometimes. It's just that they're regenerated over and over and over again. So you end up with a catalyst. In terms of energy, they provide an alternate mechanism, and that can reduce the activation energy. So we can see that here, right? One big activation energy versus many small activation energies. Me jumping up to my 2nd floor versus climbing up the steps. One big activation energy, many small activation energies, same overall start and finish. And here's another example of that. Here's one without the catalyst, here's one with the catalyst. And let's go back to one of the first things we learned in this unit, which is Boltzmann diagrams. Remember that the activation energy is kind of like the cutoff for how many molecules can actually react. So in the green case with the big activation energy, right, only this proportion of molecules can react. But in the orange case with lower activation energy, which is here, orange case, more of them. It's the orange ones plus the green ones, right? All of these can react. These ones are still out of it, but the more can react, so there's a higher chance of an effective collision. So this reduction in activation energy does two things. You can either make a process go faster at the same temperature, right? Because there's more chance of effective collisions. You've got more particles that can collide with the right energy. Or you can make the reaction go at a lower temperature than it did before, right? Because you can lower the activation energy, and now if you cool things down, this curve will shift down, but you've still got molecules that can react. And this is what our bodies do with processing sugar. So here's glucose. If you burn it, it's a one step. It's just a big activation energy because, you can tell it's a big activation energy because this paper is not on fire right now. Okay? Oxygen's hitting it. It's ready to burn. All the chemicals are there. There's just not enough activation energy to take it over the hump. Meanwhile, in my body right now, I'm digesting the breakfast I had, and that's had sugar in it. So what happens is you just have a bunch of small activation energies. And each small activation energy can happen at body temperature. And so my body can do the exact same overall reaction, but because I'm doing it in multiple steps, it can happen at 37 degrees Celsius instead of like 250 degrees Celsius with the paper burning. So yeah, that's useful. You can imagine both of these are useful for industry. You can make things go faster at the same temperature, or you can have a reaction at a lower temperature, so it can be safer if you're doing it industrially. You can make it faster and safer. Win-win. And the catalyst gets regenerated. Right? We talked about how the catalyst gets regenerated, so you don't even have to add more catalyst. You just use it forever. So yeah, catalysts in general are very, very good. What's next? I think that's our last thing. Yeah, energy density. So energy density. I'm going to pause and get that set up. So here's a practical question. Why don't we have electric planes? We have electric cars. We have electric phones. This thing goes all day, right? And it's a very small battery comparatively. Why don't we have electric planes? Well, the answer comes from energy density, the concept of energy density. Right, energy density. So think about density. Right, density is weight per volume, or in terms of normal things, weight per volume. So like this spoon is much denser than this marker. If I put this spoon in water, it'll sink. If I put this marker in water, it'll probably float. So it's not just about weight; it's about weight and volume. Here we have two types of energy density. We have gravimetric energy density, which is kind of joules per kilogram. And we have volumetric density, which is like joules per liter. Both are important. And to explain why both are important, let's think about the cell phone for a second. Right? Gravimetric density, which is this one here, joules per kilogram, is important because I don't want my cell phone to be too heavy. If I had something with a high gravimetric density, my phone would be very heavy for storing the amount of energy it takes to use it all day. Volumetric density is also important to my phone. Volumetric density is how much energy I can store per volume. And so my phone, phones try to be very, very thin. Volumetric density is important for them because if you had something with, say, a high gravimetric density, so lots of energy per gram, but a low volumetric energy density, you'd have to have a very big battery. It would just be very light. Yeah, both are important. We want gravimetric and volumetric density in our energy sources. Both would also be important for an airplane. Remember, our key thing is, why don't we have electric planes? Both are important for an airplane. Gravimetric because the airplane has to take off, right? And the heavier it is, the harder it is to take off, harder it is to fly. Volumetric because the airplane is pushing through the air. If you have a big energy source, a big power source, your plane is very, very big and it has to push through more air. So both are important for airplanes. For cars, let's think about cars. What do you think is more important for cars? Well, cars are sitting on the ground. They're supported by the wheels. So gravimetric density is not actually that important for cars, but volumetric density is, because they take up space, right? Batteries take up space. If you have something with high gravimetric but low volumetric density, your car might go very far with a small battery, it might have a lot of energy in the battery, but if it's low volumetric, then it takes up a bunch of space. You might only get one person in there or whatever. Lithium ion is pretty good at both, right? They're the best kind of electrical battery we've got right now. That's what's in my phone. You know, it's low weight and low volume for the same amount of energy. So that's why it's in my phone and it's in all kinds of things. But let's compare that to fossil fuels. So this is a lithium ion battery. Let's compare that to fossil fuels. And this is a great thing from Wikipedia. It's different energy densities. Here's lithium ion battery, 700 kilojoules per kilogram, 1500 kilojoules per liter. Let's look at gasoline. 45,000 kilojoules per kilogram, right? 45,000 versus 700 per weight. And in terms of per liter, 1500 versus 33,000. So it holds way more energy in a kilogram, and that energy fits in a much, much, much smaller space than it does for an electrical battery like a lithium air battery. So this is why we have to have fossil fuels for jet planes, because they carry so much energy in a kilogram, meaning the plane can take off, and they carry so much energy per liter, meaning the plane can be smaller and cut through the air better. Planes store their fuel like in the wings and stuff like that. Yeah, let's look at some other energy sources. Over here we got hydrogen, liquid hydrogen, hydrogen gas, and hydrogen gas. Compressed hydrogen, liquid hydrogen. It's extremely good by mass. It is by far and above the best thing by mass, right? We're looking at 140,000 kilojoules per kilogram, right? Like more than 3 times better per mass, per kilogram, than gasoline. But by volume it's not great, right? So that means if we had a hydrogen plane, the plane would be very, 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 very big. It would be light, but it would be very, very big. And so that would not work. But this does work for rockets. Rockets want to be very mass efficient, right? They have to take off and go up into space. So there are hydrogen rockets, and they tend to be the most efficient rockets. On the other side, we have things that have very, very good volume density, like aluminum, silicon, and anthracite. Aluminum in particular, it's extremely good by volume, right? 85,000 per liter. So almost 3 times better than gasoline per liter, per volume. But really not great by mass. It's maybe half of the mass density. So if I had my phone running on an aluminum battery, it would be much, much, much smaller. The battery would be much, much, much smaller than the lithium-ion battery, but it would be heavier, a lot heavier. Actually, it wouldn't be heavier, not compared to lithium-ion, but compared to gasoline, it would be heavier. Gasoline-powered phone, there's a thought, eh? So gasoline kind of hits this sweet spot of having high density in terms of both mass and in terms of volume, and that's why we're probably not going to get away from fossil fuel powered commercial air travel in any time soon. There are companies that are working on short hops, planes that can stay in the air for like an hour, that use batteries, but I think jet fuel is going to be the king of commercial air travel unless we find some kind of other energy source for air travel. I don't know, a nuclear reactor with a turbine, and who knows. The last piece for energy density, let's talk about that aluminum thing. Aluminum. Remember how I said that cars, they care a lot about the volume, but they don't care that much about the mass because they're supported by the ground. They don't have to take off and stay in the air, so they don't really care about the mass, but they do care about the volume. So one concept that's interesting is aluminum air batteries for electric cars. Aluminum has this really good volumetric energy density, so you can have a very small battery, which means your car can be very small and like really efficient and push through the air really well. It's going to be heavy, but it doesn't matter. It's a car, so then you can have a car with a small battery, and it can go like 4,000 kilometers on a single battery. Someone did the math and thought, if I take a Tesla Model S and I replace all the lithium ion by aluminum, is actually we can make that Tesla go 4,000, 5,000 kilometers on one battery. Problem is, it's aluminum air, so the air comes in, hits the aluminum, and makes aluminum oxide and aluminum hydroxide and stuff. So the air is actually reacting with the aluminum oxide. Sometimes these get Sometimes these get recharged with water too. You need water to make the hydroxide to combine with the air. So you can't recharge it. The aluminum basically rusts. You're rusting the aluminum in order to go anywhere. But the nice thing about aluminum and aluminum oxide is it can be regenerated with electricity. So you basically put the aluminum oxide into a big vat, you run electricity through it, and molten aluminum can come out the bottom. And so you can use electricity to get the aluminum back, put the aluminum back in the battery, run the battery again and again and again. And if you use renewable electricity, you've basically got a pretty decent energy storage source with probably good enough density. Like if we look at this density up here, it might actually be good enough for like a jet plane. Yeah, it's a thought. It's a thought that some people have. That's the entire lesson, so let's go back over it. We talked about multi-step reactions and the rate determining step. We talked about reaction mechanisms in terms of one-step versus two-step, and a little bit about how we know that that exists. We talked about the rate law, and especially we talked about how these coefficients don't actually relate to anything here. They are determined experimentally. We did a practice problem where we determined a rate law. We talked about catalysts, the two ways catalysts can affect a reaction. One, holding it in the right orientation, like an enzyme or the platinum. Or number two, participating in the reaction, but then getting regenerated. Participating in the reaction. And then the general thing that happens is that you get a reduction in activation energy because of the new mechanism. The new mechanism has a lower activation energy than the old one. Which means that more particles have enough energy to react, which means you go faster at the same temperature, or you can actually make the reaction go at a lower temperature than was possible before, kind of like burning glucose in our body versus burning glucose out in the air. We then talked about energy density, which we just finished talking about. Lithium-ion batteries are the best in terms of batteries right now, but they pale in comparison to something like gasoline in terms of both mass and volume efficiency. Talked about why hydrogen is not great in terms of volume efficiency, so it's not going to be good for cars, but it's great for rockets. And we talked about how aluminum is really good for volume, so great for cars. I think I might have said great for cars in the hydrogen one. So hydrogen not great for cars. Aluminum probably okay for cars. But neither of them are very good for airplanes because airplanes need both mass and volume efficiency. Hydrogen great for rockets. And then we talked about aluminum air batteries, so we just finished talking about that. So there's our review. Thanks a lot, and I'll see you guys in class.